Associate Professor in the Department of Applied Science with the Academy of Science and Technology. Hi my dear friends, welcome to the new video on complex analysis on the topic how to find an analytic function. We know an analytic function is f equal to u plus iv. If we know both its real and imaginary parts, we can easily write the corresponding analytic function. Suppose we know only its real part. Then you think how to write the corresponding analytic function. If you think, then you will get one way of writing the corresponding analytic function by finding its conjugate. Here we know only u. If we can find its conjugate v, then we have both u and v. Then you take u plus iv, we will get the corresponding analytic function. Similarly, if we know only its imaginary part, then you can write the corresponding analytic function by finding its harmonic conjugate u and taking u plus iv. This is one method of finding an analytic function. In this video, I will illustrate another method of finding an analytic function when u or v is known. And the method is Milne-Thomson method. Milne-Thomson method is a method for finding an analytic function when its real part is known or its imaginary part is known. And it is named after the English mathematician Louis Melville Milne-Thomson. As I mentioned, it is a method for finding analytic function directly from its real part or its imaginary part. Suppose we have the real part of an analytic function. Then by using Milne-Thomson method, you can easily write the analytic function without finding its conjugate. Let me illustrate it. U is given. We have to find the analytic function f of z. We know by integrating f dash z, we will get fz. So we can write fz equal to integral f dash z dz. Again, while deriving Cauchy-Riemann equations, we got f dash z is dou u by dou x plus I dou v by dou x. So you replace f dash z by dou u by dou x plus I dou v by dou x. Now fz is integral dou u by dou x plus I dou v by dou x into dz. But we know only u. So we can't write dou v by dou x. So we have to replace dou v by dou x in terms of partial derivatives of u. Since f is analytic, we know f satisfies Cauchy-Riemann equations. Cauchy-Riemann equations are dou u by dou x equal to dou v by dou y, and dou u by dou y is minus dou v by dou x. So from the second equation, we have dou v by dou x is minus dou u by dou y. So this integral can be replaced by integral dou u by dou x minus I dou u by dou y into z. See, in Milne-Thomson method, next we have to replace x by z and y by 0. Wherever you find x, you replace it by z, and wherever you find y, you have to replace y by 0. Then you can see the integrand is a function of z alone. So you can easily integrate with respect to z. After integration, you put a constant c. That will be the required analytic function f. One more situation is there. Suppose the imaginary part is known. We have to write the corresponding analytic function without finding its conjugate. We know fz is integral f dash z dz, and you replace f dash z by dou u by dou x plus I dou v by dou x. Here our situation is imaginary part is known. So you replace dou u by dou x in terms of partial derivative of v with respect to x or y. By Cauchy-Riemann equations, we can replace dou u by dou x by dou v by dou y. So we have integral dou v by dou y plus I dou v by dou x into dz. Again, in this method, we have to replace x by z and y by 0. Then you can see the integrand is a function of z alone. You integrate with respect to z, and after integration you put a constant, and that is the required analytic function. And this is the method of finding an analytic function when its real or imaginary part is known. And this method is known as Milne-Thomson method. Let me illustrate a few problems how to construct an analytic function by Milne-Thomson method. Consider the question. Find an analytic function whose real part is e raised to x cos y. See, in the question, the method is not mentioned. Only u is given. We have to find the analytic function. Really, there are two methods. If you find its harmonic conjugate b and taking u plus iv, we will get the required analytic function. Another method is by Milne-Thomson method. Among these two methods, Milne-Thomson method is the easiest method. Here u is given. So you have to find its partial derivatives with respect to x and y. We have f z equal to integral f dash z dz. We know f dash z is dou u by dou x plus I dou v by dou x. Here we have to replace dou v by dou x in terms of partial derivatives of u by using Cauchy-Riemann equations. It is very clear dou v by dou x is minus dou u by dou y. So integral becomes integral dou u by dou x minus I dou u by dou y. You replace dou u by dou x and dou u by dou y, then we have integral e raised to x cos y plus I e raised to x sin y dz. In this method, next we have to put x equal to z and y equal to 0. So the first term becomes e raised to z since cos 0 is 1. And second term is when y is 0, sin y is 0. So second term will be 0. So integral becomes integral e raised to z dz. Its integral is e raised to z after integration plus c. So we have f z equal to e raised to z plus c. Next question. Find an analytic function whose real part is x cube minus 3xy square plus 3x square minus 3y square plus 1. Here u is given, so you find dou u by dou x and dou u by dou y. Here dou u by dou x is 3x square minus 3y square plus 6x. Dou u by dou y is minus 6xy minus 6y. We have f z equal to integral f dash z dz, that is integral dou u by dou x plus I dou v by dou x into dz. By applying Cauchy-Riemann equations, we can replace dou v by dou x by minus dou u by dou y. So integral dou u by dou x minus I dou u by dou y dz. Next replace dou u by dou x and dou u by dou y. We have integral 3x square minus 3y square plus 6x plus I into. Here both negative signs become plus. That's why it is plus I into 6xy plus 6y into dz. Next you put x equal to z and y equal to 0. So integral 3z square plus 6z dz. Because when y equal to 0, 3y square is 0, 6xy is 0, 6y is 0. So now the integral becomes integral 3z square plus 6z. Its integral is z cube plus 3z square plus c. So the required analytic function is f z equal to z cube plus 3z square plus c. Consider the next question. Find an analytic function whose imaginary part is cos x cos hy. That is, v is given. v is cos x cos hy. You find dou v by dou x and dou v by dou y. We have f z equal to integral dou u by dou x plus I dou v by dou x into dz. By Cauchy-Riemann equations, we can replace dou u by dou x by dou v by dou y. So integral becomes integral dou v by dou y plus I dou v by dou x into dz. You replace dou v by dou y and dou v by dou x. Next you put x equal to z and y equal to 0. Here, remember, sin h0 is 0 and cos h0 is 1. When x equal to z and y equal to 0, the first term becomes 0 since sin h0 is 0. In the second term, cos h0 is 1. So, second term will be sin z. So, integral becomes integral minus I into sin z dz. You take the constant minus I outside. Integral sin z is minus cos z. So, the answer is I cos z. After integration, plus c. So, the required analytic function is f z equal to I cos z plus c. Let me solve one more question. Question is, find an analytic function whose imaginary part is e raised to minus x into x cos y plus y sin y. Here v is given. For the convenience of differentiating v partially with respect to x and y, we have to open the bracket. So we can write v as v is equal to e raised to minus x into x cos y plus e raised to minus x into y sin y. Next, we have to find the partial derivatives of v with respect to x and y. So, for dou v by dou x, you consider the first term. While differentiating partially with respect to x, we have to keep y as a constant. So, in the first term, cos y is a constant. So, we have to differentiate only e raised to minus x into x. See, it's a product, so you have to apply the product rule. Product rule is first function into derivative of second plus second into derivative of first. This is product rule. So, dou v by dou x is, in the first term cos y is a constant. So, cos y into, you have to differentiate e raised to minus x into x by using product rule. So, its derivative is first function e raised to minus x into derivative of x, it is 1. So, e raised to minus x plus x into derivative of e raised to minus x, which is minus e raised to minus x. So, the term is minus x e raised to minus x. Plus, next you have to write the derivative of the second term with respect to x. See, in that y sin y is a constant. So, you have to differentiate only e raised to minus x. Its derivative is minus e raised to minus x. So, derivative of the second term with respect to x is minus e raised to minus x y sin y. So, we have dou v by dou x is cos y into e raised to minus x minus x e raised to minus x minus e raised to minus x y sin y. Next, dou v by dou y. Here we are differentiating v partially with respect to y. At that time you have to keep x as a constant. You consider the first term. In the first term, e raised to minus x is a constant. So we have to differentiate cos y only with respect to y. Derivative of cos y with respect to y is minus sin y. So derivative of the first term is minus e raised to minus x into x sin y. Next, derivative of second term. See, we are differentiating with respect to y's. Here, e raised to minus x is a constant. So, you have to write the derivative of y sin y. See, it's a product, so you apply product rule. So, its derivative is e raised to minus x into y into derivative of sin y, it is cos y plus sin y into derivative of y, which is 1. So, we have dou v by dou y is minus e raised to minus x into x sin y plus e raised to minus x into y cos y plus sin y. Next we have f z equal to integral f dash z, which is integral dou u by dou x plus I dou v by dou x into dz, which is dou v by dou y plus I dou v by dou x into dz by using Cauchy-Riemann equations. Next you replace dou v by dou y by minus e raised to minus x into sin y plus e raised to minus x into y cos y plus sin y. And replace dou v by dou x by cos y into e raised to minus x e raised to minus x minus e raised to minus x y sin y. I didn't mention since it is too lengthy. You have to replace this dou v by dou y and dou v by dou x. Next you replace x by z and y by 0. While replacing y by 0, you have to keep in your mind cos 0 is 1 and sin 0 is 0. So in Vy, the first term is 0 since sin y is 0. Second term is also 0 because in second term there is y cos y. When y is 0, the term is 0. Third term in Vx. in third term in dou v by dou y is e raised to minus x sin y. When y is 0, sin 0, it is 0. So the three terms in dou v by dou y are 0 when you put y equal to 0. Next, in dou v by dou x, the first term reduces to e raised to minus z, second term minus z e raised to minus z, third term is 0 since there is y into sin y. When y is 0, that term will be 0. So you can see the integral becomes integral I into e raised to minus z e raised to minus z dz. Since I is a constant, you take it outside. So I into e raised to minus integral e raised to minus z e raised to minus z dz. You split the integral. So you can see it is I into integral e raised to minus z dz minus integral z e raised to minus z dz. You have to integrate both integrals. The first integral is very easy and its answer is e raised to minus z by minus 1. That is minus e raised to minus z. So integral of the first term is minus e raised to minus z. Minus of, you write integral of the second term. See, it's a product, so you apply integration by parts. And you can see integral z e raised to minus z is minus z e raised to minus z minus e raised to minus z. Next you open the bracket. You can see it is I into minus e raised to minus z plus z e raised to minus z plus e raised to minus z. See, e raised to minus z will cancel each other. And after integration you put a plus c. And you can see our analytic function f z is I into z e raised to minus z plus c. See, this is the required analytic function whose imaginary part is e raised to minus x into x cos y plus y sin y. Thank you.